atmosphere. It covers how the Earth's atmosphere has changed over time and how the carbon cycle helps to maintain the atmospheric composition. It also looks at the sequence of rock formation and weathering. First, how the Earth's atmosphere has changed over time. Watch the next clip and note down the stages in the evolution of our present-day atmosphere.
The Earth's temperature varies between night and day, from one season to another, and from the poles to the equator. But our planet has an average global temperature of about 15 Celsius. The Earth is kept warm by the gases in the atmosphere. Without them, it would be over 20 degrees below zero, which is far too cold to support life.
We don't know for certain how the early atmosphere evolved, but we can make intelligent guesses based on evidence from rocks and fossils. We think that about 4,600 million years ago, the Earth evolved from a swirling mass of dust and gases, just like Jupiter is today. The early Earth would have been a molten mass of volcanoes and hot magma. We think that its atmosphere would have consisted mainly of carbon dioxide and water, because these are the gases given out by volcanoes today. Levels of oxygen built up very slowly. When there was enough, about 600 million years ago, then life exploded on this planet, and since then the atmosphere has hardly changed at all.
So the early atmosphere was mainly carbon dioxide and water, gases which escaped from volcanoes. Once plant life appeared on the Earth, the level of oxygen built up slowly. Atmospheric nitrogen came from another volcanic gas, ammonia. For the last 600 million years, the Earth's atmosphere has hardly changed. One vital function of the atmosphere is to keep the Earth at a steady temperature. Watch the next clip and see how it works, and the special term we use to describe the process.
The Earth's atmosphere helps it to retain energy which arrives from the sun in the form of electromagnetic waves. Most of these waves have very short wavelengths, like the ultraviolet radiation which gives you a suntan. Some radiation is reflected back into space, but most of it is absorbed by the Earth's surface. This has a warming effect. Like any warm object, the Earth's surface radiates heat. The radiation goes back out towards space, but this time the radiation is of a longer wavelength. It's in the infrared part of the electromagnetic spectrum. This results in a cooling effect, but some of the infrared waves are trapped by certain gases in the atmosphere. This radiation is then re-emitted, and some of it gets back to the Earth's surface, so the atmosphere keeps the Earth's surface warmer than it would be otherwise. This is the greenhouse effect. Overall, the Earth and its atmosphere receive and give off exactly the same amount of radiation, so the Earth stays at a steady temperature. But without the greenhouse effect, this temperature would be much lower. The atmosphere is 78% nitrogen and 21% oxygen. The gases that cause the greenhouse effect are contained in the remaining 1%. The main ones are carbon dioxide, methane, and water vapour. Although the greenhouse gases form a tiny proportion of the atmosphere, they are vital to our survival.
So it's the layer of carbon dioxide in the atmosphere that keeps the Earth at a steady temperature. This is called the greenhouse effect. Next, how the carbon cycle helps to maintain the composition of the atmosphere. The next clip explains the role of the carbon cycle and the important part played by the oceans.
The oceans cover over 2/3 of the Earth's surface, and we now know that they have a major effect on the Earth's climate. They're important because they store heat in the ocean waters and then transport it around the Earth in ocean currents. They also contain large amounts of carbon, both as marine plants and as dissolved carbon dioxide in the water. This interacts with carbon dioxide in the atmosphere, with marine plants that live on the ocean's surface, and with sediment at the bottom of the ocean to form part of the very complex carbon cycle.
The level of carbon dioxide in the air depends on many different processes. Photosynthesis uses carbon dioxide as a raw material to produce sugars, so plants take carbon dioxide out of the atmosphere. Both animals and plants get their energy by respiration, a chemical reaction which releases carbon dioxide into the atmosphere. Carbon dioxide dissolves in the ocean, but this is a two-way process. When the sea gets warmer, some of the carbon dioxide comes out of solution and passes back into the atmosphere. Natural processes like these balance out, so that the tiny percentage of carbon dioxide in the air is maintained. But human activity is now increasing carbon dioxide levels.
So the carbon cycle of respiration and photosynthesis among animals and plants maintains a constant level of carbon dioxide in the atmosphere. There's also concern that burning fossil fuels, like coal and petrol, is increasing the amount of carbon dioxide and causing the Earth's temperature to rise. That's global warming. Others say that global warming is just one of the many natural long-term temperature changes that have happened throughout the Earth's history. The next part looks at the sequence of rock formation and weathering that makes up the Earth. There are three types of rock you need to know about. They are igneous, sedimentary, and metamorphic. These rocks are linked to each other by the rock cycle. The next clip explains how it works.
When a volcano erupts, it's the beginning of one part of something known as the rock cycle. There are three types of rock in the Earth: igneous, sedimentary, and metamorphic. Volcanic rock is called igneous rock, and igneous comes from the Greek word meaning fire, and that's where it's coming from.
Molten rock, hotter than fire. But how is it hot? The centre of the Earth, the core, is thousands of degrees Celsius. It's hot enough to make molten rock, which is what the next layer, the mantle, is made of. The Earth's skin, or crust, is anything from 5 to 75 kilometres thick. It's cooler, and so it's solid. Sometimes the molten rock pours out through volcanoes.
This is brown sugar in water. When heated, it becomes like toffee. But when I pour it on this tray, it cools and solidifies like molten rock. And this is what happens with igneous rocks. Igneous rocks have a crystal structure, and the size of the crystals depends on how quickly the rock cools. The quicker it cools, the smaller the crystals. Now, once the rock is outside, things begin to change, and this is due to the weather.
Rainwater gets into the cracks and freezes. The ice expands as it forms, and the force is large enough to split the rock.
Eventually, the rock has so many cracks. This has been very well weathered. Easy. But what happens to the bits of rock that break off? Over the years, bits of sedimentary rock settle on the seabed because of gravity, and the layer gets to be very thick. And the thicker the layer gets, the more pressure is exerted on the bottom of it.
As the particles get squashed, the water is squeezed out, leaving deposits that cause a process called cementation, where the particles are cemented together. Over time, the squashing and cementing of the sediment forms sedimentary rock.
Rocks made of sand that have been compacted and cemented are called sandstone, like the walls of my cave. This means that this cave is in an old sea or lake bed. The water disappeared long ago, and the process takes millions of years. So this sandstone is 235 million years old. Washed in with the sand are shells and other organisms, and they get squashed as well to form limestone. And limestone is another sedimentary rock. This is limestone, but this is not the end of the story. After this sedimentary rock's made, the weight of the layers pushes them deep underground, where the earth can heat and squash the sedimentary rock further. Now, when it does this, the rock changes yet again, and this third type of rock is called metamorphic. Both sedimentary and metamorphic rocks can work their way to the surface and be eroded by the weather and make their own rock cycles. The other possibility is that metamorphic rock can get heated and melted down, ready to be thrown out of the earth again to make igneous rocks. So the whole thing starts again. That's why it's called a rock cycle.
So, over millions of years, igneous rocks are eroded and weathered, transported and deposited to become sedimentary rocks, which under heat and pressure can become metamorphic rocks. Metamorphic rocks can either erupt back to the surface as igneous rocks, or be exposed or lifted to the surface by movements of the Earth's crust to complete the cycle. Igneous rocks are the oldest rocks on the Earth. They were first formed when the molten Earth began to cool down and solidify. Examples of igneous rocks are granite and basalt. Sedimentary rocks are younger. They are deposited in layers made from eroded particles of igneous rock and other material. They're changed into solid rock by pressure and heat, compacting and cementing the lower layers. Examples of sedimentary rock are limestone and sandstone. Metamorphic rocks are made from other rocks by great pressure and heat. Examples of metamorphic rock are marble and slate. Here's a question about the rock cycle. Name the process taking place at each of the labelled stages of the rock cycle. Process A is weathering. Process B is transportation. Process C is sedimentation. Process D is cementation, where rocks are forced deep underground. Process E is where rocks erupt again or are pushed to the surface by uplift or folding. That's the end of the whole section on changing materials. This section is about patterns of chemical behaviour. It's divided into the periodic table, chemical reactions, rates of reaction, and energy transfers in reactions. First, the periodic